In this explanation, I would like to hopefully shed some light on how do we do the avoiding of inverse crime by computing tomographic data using higher resolution and downsampling it or interpolating it down to a coarser resolution. And it goes pretty much like this. Let's start from how we think about the problem, and then let's see how MATLAB is looking at the problem. So for us, the situation is that we have we are working in square. Now I don't remember, did we do this? I think we did this on, so that this goes from 0 to 1. Did we? Let me check. Yep. So we were thinking about the image domain being this one, and then we take X-ray images of what's inside. Let me have one color for X-rays. So we are thinking that we have a detector, let's say here, for a given direction of X-rays perpendicular to the detector. So we are thinking of measuring data like this. So we have some function here inside. We have some angle. We have a detector that has, let's say, starting from point from here and ending point, let's say the detector's length is L. So we have a one-dimensional parameter S running from 0 to L, giving information about which X-ray it is. So we have an angle, we have a position of the detector in the space, we have a distance along the detector up to some point, and then we know, because we know the angle, there's an angle of the X-ray and a position here. So then this number and this number will specify which ray are we looking at. Then, because we are doing computational work, we divide our area into pixels. And now in the coarse resolution, let's say we have 4 by 4 pixels in this simple example. And then we are dealing with the data. So for given phi and S0, we know that the ray travels inside these pixels, these lengths, and that we use in our computational model. But now we want to do this trick of measuring at a higher resolution, so to avoid inverse crime. So we don't want to use the matrix built for this exact 4 by 4 discretization. We actually want to measure some data with twice finer resolution, compute that data, and then somehow project it down so that it would be picked up from the coarse grid data. And this way our data will be modeled with a different model than the one we use in the reconstruction. So in this case, we have more of these little lengths here going through these smaller pixels. So this is the geometry we are thinking of. We would like to use this finer grid to compute the data for our given phantom. the rectangles we built, compute them at some points along the detector, and then we would like to look at the computational model on the coarser grid, the blue grid, and see at which points we wish to measure here, because when we use this finer model, let's say we simulate the X-ray measurements at some points along the detector. So we have those numbers from the fine grid model, and then we want to simulate measurements from the blue resolution at some points that may be a little bit different. Let's keep that freedom that there's some set of points we are dealing with the coarser resolution, not necessarily the same points. But once we know the measurements at these red points, we can then interpolate from the knowledge of the data at red points, we can interpolate it to the blue points. Or that is what we will do. Yes?
Does it mean like a different number of X-rays, or do they hit like a different part of the detector?
Yes, we use the same number of X-rays, but they hit a different part of the detector. That's what will happen. Yes. Yes. And no, I think, yeah, actually when we do this modeling, yes, we do have more X-rays actually. And they will hit, yeah, different parts of the detector, and they are not necessarily even overlapping like every second one of them, for reasons I will explain next. So this is what so yeah, maybe let's have more of these red points. So we simulate on the red points, and then we want to interpolate on the blue points, and then the values at the blue points will not be given by the matrix related to the blue discretization, which would be the inverse crime, but that's what we don't do. There will be several little interpolation errors and approximation errors which make sure that we are not doing inverse crime. Okay. I see some wondering expressions. Any questions before I go to the next one? Yeah.
When do we do this kind of thing? Is it just like testing that the method is working right? Or?
Yes. So the thing is, let's say our goal is to build a reconstruction method for real tomographic data, which really is our goal, because that's what will be done later in the course and in the project works. In my view, it's important when building a method that is supposed to work with real data. I think it's a good idea first to test the method with simulated data, because then you know perfectly the structure of the data and where it came from, and it makes debugging and looking for errors easier, because there are no very unexpected errors, which real world always provides you. So it's a good idea to do first reconstruction with simulated data before going to real data, because then you have better control of where possible problems are coming from. However, testing an inversion method with simulated data has to be done carefully, because if you do inverse crime, I mean if you have the computational model like this, and in your simulation, if you just choose some f and multiply the matrix A to get m for the chosen f, and then you try the method by inverting from m and trying to go back to f. Like we saw in the computations, if we use the same A matrix for simulating the data and for computing the reconstruction without adding noise, sometimes we get very good reconstructions, perfect reconstructions, but this is not true. This is not really, this is a deception only. This is the inverse crime, because what happens then is that in the simulation process and inversion process, exactly the same matrix gives that the numerical computations may somehow nicely resonate with each other, so that it gives really perfectly the correct floating point numbers back, even if the matrix is ill-posed. But this is not good because this result will break down completely when you move to real data. Because it will even break down if you add a little noise. Like I hope I have demonstrated with the computations. So that's why it's important to test any reconstruction method with simulated data where inverse crime has been avoided, so that we don't get these unrealistically good results from inverse crime data. Only after testing the method with simulated data without inverse crime, we are confident enough to take the step to go to real data. I'm not sure, did this answer the question at all?
Yeah. Yes.
Okay, good. So that's how the thinking goes. It's important to do simulated data, but it's important to do it as realistically as possible. So that's the aim here. So that's why we want to simulate at the higher resolution, get some data, interpolate it down to these blue points, so that the blue data is not coming directly from the blue, the matrix corresponding to the blue grid. So somehow maybe if so let's put it this way. So we have an F which we could multiply with this matrix, and we would get this one, but here we have inverse crime. Should have been blue. Sorry. If we do this, there would be inverse crime. However, what we do is this. We take the same F with a higher resolution, though maybe this should also be, yeah, this should maybe be like this, yes. So then we go to higher resolution, we take kind of the same F, but with the higher resolution. We multiply it by the matrix A coming from the higher resolution. We get a vector M, which we downsample or interpolate so that it becomes of the same size than this one. And that we will call like as if coming from a continuum model or kind of a better model or finer model. So then we use this one in the inversion based on the blue matrix, and that's a much more reliable thing to do. So far I'm not sure if this explanation is explaining or confusing more. So anyway, this is what we would like to do. However, how MATLAB thinks. How MATLAB thinks is that for the blue case we have this situation, and MATLAB's radon will put the origin of the coordinate system to the middle pixel, which, because the middle point of our matrix is not a pixel, it will choose one of these 4 pixels, and actually it will choose this one. And it will put the origin here. So this is the coordinate system like this. And really this is 1. So actually the x coordinate of this, so this point here would be 1/2, and the y coordinate minus 3/2. So this is how MATLAB is looking at the situation here. And for the
Or I remember at some point you said that it might be other way around this. Why?
I'm not completely sure. I'm not completely sure. So let's. It's one of those options. I don't remember clearly, but I hope the explanation will still. I hope the explanation will help. We'll see. This is the finer grid, and again MATLAB takes this to be 1. Well, this should be squares, but there's a little deformation. But anyway, so MATLAB is taking the pixels to have the same size, and again it will go to the middle pixel, again define one of these 4, and now it's here.
Shouldn't be like the upper left one. I mean, if it's counting from up and from left, and I think it's supposed to do the same thing. So
yeah, I think I did some testing. It was a long time ago, but I as far as I remember, it's this one. It should be checked actually from the MATLAB code which one it really takes. This is how I remember it goes. I may be wrong, but I mean, it's the way MATLAB thinks. It takes one of these 4 pixels, and for the sake of this explanation, it doesn't really matter so much. The main point is that it's not in the middle. The main point is that MATLAB origin for the blue case is here. MATLAB origin for the red case is here. It's different. That's the point. Maybe it's not exactly those pixels, but anyway, the origins are not in the same place. That's the main point here. And then if we use the same angle phi I was showing here, so then what MATLAB is doing with the angle phi, I think it always takes the ray that's going through the origin, and then it will take the next rays so that the distance between the rays is the pixel width. So this is 1, the distance between them. Like this. So we have here a blue detector with points like this. And MATLAB takes this S coordinate along the detector. Here, this ray going through the origin, this is S equals 0, and then this is negative S, this is positive S. So there's an S coordinate for each of these points. There's an S coordinate. That's the one we wrote like this. We took the sinogram and S equals radon F and the angles. Remember, we wrote this in MATLAB. So the S vector here is the vector of the coordinates of along this detector. That's what the S is. Now, in this case, again, MATLAB is taking with the same angle phi, so there's the angle phi, still the same angle, so there's the line, and then again the distance between these guys is 1. There are more, like you asked, there are more rays now, and again there is a detector, maybe now it's a red detector. Again, here is S equals 0. And now you see in MATLAB the geometry is completely different. This square is smaller than this square, first of all, because in both cases the pixel side is 1. So MATLAB is computing in different sized sized squares? Well, of course, we can think of shrinking them into our unit square, no problem. However, the choice of rays is different. There are two origins, and the origins will also define where the 0 point of this S line is. So that's why if we look at 45-degree angle, then you see these two origins are actually mapped at the same point. But when we turn our tomographic device, the simulated tomographic device, if we are looking at rays to this direction, then you see that the two origins are mapped into different places. As you can easily imagine, when this thing is going around, well, here they are the same point, here they are different. It's something related to sines and cosines. How far are these 2 points from each other? So now we, from MATLAB applying radon to our F, we are applying radon to the 32 by 32 F with a set of angles, and then to the 64 F with the same angles. What we get here are different size sinograms, because there's a different number of rays. There are more rays in this case. And the S numbers are also different, because even the origins are different, and this detector is longer. So when we want to do this one, all the time thinking about the unit square, the same square, but different pixelizations. And the tool we have from MATLAB is radon, which is doing stuff like this. That's where those technical lines in the MATLAB file come from. I did spend some sweet hours coding it up, I must say. Yes?
So, I mean, if we have high resolution, could that even be a good thing that the origin isn't at the same point? Because then we could somehow be avoiding inverse prime. I don't know if it's too much when it moves. The object kind of moves in the, you know, your device.
Right.
But if we have this little resolution, it's too much. You know, then it moves like really in big area.
Yeah, the thing is actually that I think it's better to think that the object doesn't move. The object is in the same place, but what X-rays we simulate, it will change, because when we go around, like there are these two origins, the set of X-rays will, and their coordinates will be, the numbering system and the coordinate system will be kind of changing depending on the resolution. I think it's more helpful to think that the object is in place, but we measure with less or more rays, or the higher the resolution, the more rays we have, and then they are parameterized differently, and the coordinates, the angles are the same, but these S values also change in these ways.
Okay,
and
but I just think, would it be a good thing that, you know, if we want to avoid inverse prime, that we shouldn't do as much? Or if we want to avoid it, how about just taking what's the opposite of even?
Odd.
Odd, not odd, like 5 by 5, then the center point would be always the same.
But even then we would have a different number of rays,
Yeah, but
and they would hit different points in the detector. So anyway, there would be an interpolation step.
yeah, interpolation. But yeah,
And I think the thing with the different origins, I think the main effect it has in this context is that the set of the red points and the blue points, they are just kind of shifting a little bit depending on the angle. And if we would use like odd by odd, then they wouldn't shift, but there would still be a different number of them.
Yeah,
So, yeah.
You know, triple that points or some other, or it will be higher.
It could, yeah, it would be possible, yes.
Then you wouldn't need the interpolation. I think they would.
Yes.
Yeah, but that would be.
And in that case, that would be maybe a bad thing, because the whole idea of avoiding the inverse crime is to introduce a little bit of mismodeling or a little bit more modeling errors in how we build up the data. So in that sense, it kind of is good that we are using a little bit incompatible, but not too much. The idea here, at least how I was thinking when building this inverse crime avoidance strategy, was that when the resolution gets finer and finer, then the two data sets become closer to each other. I think that's somehow important. And I think that's what's happening with this approach. Yep.
So just to double check again, this, when you have this ms random function,
Yes.
s returns the number of rays?
No.
Or
No. The length of S is the number of rays, and the length of S, but S actually, it gives these, so for example here, I think this would be -1, this would be -2, -3, I think.
Doesn't know so can you return like the coordinates of S or the values at S?
It just there's just one vector which will be the same for any angle. It's just the coordinates along this one-dimensional S space. That's what it is, and I actually think it should be integers. We can check. I think that's how it is.
well, if the length, I mean the distance between the rays is 1 and
Yeah.
s is 0 of one of the points. Then.
I think that's the way it goes. Let's check in MATLAB. If I said something completely incorrect or not. Let's see. But anyway, that's the business. I just wanted to give you an idea. Why is there such a bunch of technical lines in the code? It's trying to make this happen with the tools like that. And it is confusing, and I definitely will not be able to explain this perfectly right here. Sorry for that, but I think for really understanding what's going on, you need to study the code better and think about this picture. It's not so fresh in my mind that I could really pull off really explaining it perfectly. So I think let's return to the code and see what happens there.